All right, so if we take a look, like I said, we're going to solve application problems today of exponential functions. We talked about a little bit on Friday about types of applications. Now we're going to actually get into them. One quick specific thing as we go into that, don't forget, you may want to write this down. General form of an equation. Oh man, my smartboard's way off. Y equals a times b to the x. Y equals a times b to the x. Where, remember, and then we added in the shifts and all that stuff, but remember, a is your initial value. That's your starting point. And remember, b was your multiplier. Okay, what are we multiplying by every time? And how many times am I multiplying by it and all that kind of stuff? Refresh my memory. How do you know when you've got an exponential function? What has to be true? Like we talked last Friday, that x squared is not an exponential function because it has an exponent in it. Right? Good work, group. You've got to have a variable in the exponent. Okay? Anytime there is some variable in the exponent, you know you have an exponential function. Okay? If you're looking at the equation. Otherwise, we looked at data and we said when you've got that repeated multiplication, that's what makes something exponential. That's our b value. We talked about that. And today we're going to get into those applications of that. Okay? So application number one is money. Okay? When you go through and money works off of interest, grows, and we talk about compound interest. So there's two formulas I'm going to give you. Formula number one is right here at the top. Okay? Compound interest, the idea of compounding interest is this. If you go through and you put money into an account or wherever you put the money, the idea is when you compound interest, you take the interest for a year, and let's say most banks, for example, on like a savings account, would take whatever your interest rate and compound it quarterly. So they take that interest rate and they divide it by 4, and then at the end of each quarter, they give you that amount. Okay, so for example, let me just make up some numbers that are nice. Let's say we have a 4% interest rate. If your bank is compounding quarterly, at the end of quarter one, then they'll give you 1% interest on whatever money you have, and they'll put that into your account. At the end of the second quarter, they'll give you another 1%. So that over the course of the year, that's where the 4% comes from. If you're compounding monthly, then at the end of every month, they take some money and they put it in for interest and they add that in. And the idea is, the more money you can get into your account, the quicker it will grow. Okay? So the more times you can compound it, the more money you've got there, the quicker that money will then grow. That's where like all retirement, when you've heard of like a 401k or IRAs or any of that kind of stuff, when you put it into the stock market, that's the idea, is you're trying to get that money to grow so that by the time you retire, you've got some money to live off of. Okay? So this is number one. We'll go through the different variables here in just a second. Okay? Second version is something that's, and here's the key word, continuously compounded interest. Okay? Anytime you see that word continuously, it means basically that the clock is always running. Okay? So you're earning interest every second. Or it could be the other way, by the way, rather than earning interest, maybe it's like a credit card company or something where you owe money and they're charging you interest. Okay? And the clock is running. But the idea of continuously compounded interest is one where you're constantly earning or owing money. Okay? And in that case, anytime you see that word, you go to what I'm going to call the Pert Formula. Okay? You should have seen this at least a little bit last year when you were talking about exponential. So if you notice, here's what everything is. P in both of those formulas stand for your principal. It's your starting amount. How much money do you put in the account? How much money are you starting with? R is your interest rate written as a decimal. Okay? And I'll give you some examples here in a second, but R is your interest rate as a decimal. N in the formula, in the top formula. N is the total number of times that you're compounding per year. So again, quarterly would be 4 times a year. Monthly would be 12 times. Daily would be 365 times. Okay, and so on. T is the amount of time. So let's say you put some money into an account, you come back 10 years later, okay, T would be 10 then. Okay, and you see how much money is there now, or 5 or 2 or whatever it is. But usually in years. And then the last part, A in both of those formulas is kind of your ending amount. It's the amount of principal plus interest, okay, that you either earn or owe. I'll give you an example of one of the biggest places you'll ever owe interest in your entire life is when you buy a house. When you're paying off interest for 30 years, you end up paying more for interest than you actually pay for your house, usually, okay? You pay about twice as much interest than you do for your house because of that clock running and that idea. So this is the concept. Let's give you an example. Okay, so here's example number 1. You've got a rich relative that puts $25,000 into a trust fund, compounded continuously at 8.75% when you were born. And you come back on your 25th birthday. Let's say they set a rule that you can't touch it until you're 25. You come back on your 25th birthday and you're trying to figure out, well, I had $25,000. Let's see how much I have now. Okay? First question, out of the two formulas that we just talked about, which one am I going to use? The first one or the second one? Why second one? Continuously. There's the key word. Okay? If it would say compounded whatever, quarterly, annually, whatever, then you know you're using the first one. So we are going to use the Pert formula. And fill in the information that we know. And then the nice part is then we can go to the calculator and get an answer. So if we're trying to find the balance, we're trying to find A, the ending amount. Okay? Principal plus interest. So we're going to leave that alone. A equals. What's P in this problem? That's the $25,000. That's our principal. That's what we're starting with. So $25,000 times E, okay, the number E, like we talked about last Friday, raised to the R times T power. Interest rate as a decimal. What is 8.75% as a decimal? 0.0875. Okay? So I'm going to put this in parentheses here. We've got 0.0875 times, what's T going to be on this one? 25 years. Okay? 25 years later, we're going to come back and see how much we got. So there's the setup. The nice part is there's no solving because we're finding the ending amount. So I don't have to solve for a variable. It's already by itself. I just need to type it into the calculator. Okay? And so as you go through and you do that, let me type this in. 25,000 times, remember E is on the left-hand side. If you see right next to the number 4, there's the LN button. Right above that in blue is the E to the X. That's the E where you're going to use. So you're going to hit second and the LN button. And that's, oops, I don't have it up here. But it says E raised to some power. And then just make sure you type this whole thing in as the exponent. Okay. So if we type that in, 0.0875 times 25, and we go through and we hit enter, and that $25,000 that we started with, 25 years later you come back, and you should now have $222,000. $822, and if we're rounding based on what makes sense, since we're talking about money rounded in your cent, okay, which in this case would be 57 cents. So you started with $25,000 when you were born, and you came back 25 years later and had $222,000. Now, one of the things I'll tell you in terms of money, there's two things that affect you the most. And one we kind of talked about already. The more money that you can get into an account early, once you get money in, then it can start building on top of itself. That's the idea of the exponential growth. This one's a little unrealistic for couple reasons. Almost never do you have something that compounds continuously. Okay? So the clock is never always running, where you're always earning interest on top of interest. Okay? So that's a little bit unrealistic. The other part is the 8.75%. That's way high. Okay? Normally, I want to say right now, anybody know off the top of their head? Like, if you just put something into a savings account, I want to say savings accounts are like 1%, maybe. It's really low. Like you're going to earn almost nothing if you put something into a savings account. That's why financial advisors tell you not to just put something into a savings account and to instead put it into the stock market, put it into an IRA, something like that, because that money will grow as you go forward. But at least there's the general idea. So there's example number 1, taking money and trying to get it to grow very, very quickly. All right, let's go to the next example. A radioactive decay, a half-life problem. If we're looking at radioactive decay, we've got some radioactive element that has a half-life of 25 years. Once it's discovered, you're starting with 20 grams of whatever. How much is left after 40 years? Again, a little bit of background information. A half-life, if you're not familiar, means that however long, in this case 25 years, you will have half of whatever you started with will be left. 25 years after that, you'll have half of that amount. And then half of that, and half of that, and half of that every 25 years. Okay, so that's kind of the decaying process. So in this case, we're just going to go back to the usual y equals a times b to the x. What's the a value? What is it? I think somebody said it. 20. A is still your initial amount. Just like in the other compound interest formulas, P was the principal. That was your starting amount. That was just like the A value. So we're starting with 20 grams times, what's the B value? What's my multiplier here? It's a half. Because you're always taking half of what you started with. Okay? So your multiplier, that's why a half-life problem, your multiplier is 1/2. And then in this case, when the power that you're raising it to, the power is representing how many times are you using the multiplier, how many half-lives. That's what the exponent is going to represent. So in this case, what am I going to put for a power, or how do I find it? If I want to know how many half-lives I'm going to use. What do I do? Divide what? Yeah. We want to figure out how much is left 40 years later, but the half-life is every 25 years you're going to be taking half. So if you take 40 and divide it by 25, I believe you get 1.6. Okay. You could leave it as a fraction if you want. In this case, that's your exponent, the 1.6. 40 years later, you're 1.6 half-lives in. One full half-life, and then 6/10 of the way through the next half-life. And again, the nice part is once you've got everything set up, you go to the calculator and you plug it in. There's nothing to solve for. So y equals, what'd you get? What does this one equal? I want to say 6 points. What is it? 6 point something? I think it's 6. I think it should be 6 point something. I just don't remember what.
Yeah, 6.5975.
Okay, so we'll go 6.6. Perfect. 6.6 grams approximately. Okay? So you started with 20 grams of whatever this radioactive substance is, and 40 years later, there's 6.6 grams left. This, again, is something that obviously scientists need to keep track of, because if you're dealing with radioactive substances, you need to know when is it basically gone. Okay? That's why they're kind of keeping track of this. So when is it safe? So there's a second application. Half-life type problems. Exponential decay. Last one is population. Whether it's human population, in this case, this is population of bacteria. Okay? Could be a virus, could be, like I said, could be bacteria growth, that kind of stuff. But in general, also growing very, very rapidly. Once again, y equals a times b to the x, if you think about it that way. What's my a value on this problem? Yeah, you're starting with 1,000 bacteria. Okay, so that's your initial value, that's your a value. Times, what's the b value? What's our multiplier? 2. because it's doubling in this case, every 3 days. But because it's doubling, we're multiplying it by 2 every time. And again, if you think of the exponent as how many times are we doubling, okay, kind of like you did with the half-life, what's the power going to be? 10. Why 10, Cooper? Because you're going 30 days and it's doubling every 3, so it's going to double 10 times over the course of 30 days. So our exponent will be 10 in this case. Once again, you type it into the calculator once you get it set up correctly. And what is this one? It's a big number, I know that. So you end up with, you started with 1,000 bacteria. 30 days later, 1 month later, you have over 1 million bacteria, okay, whatever you're dealing with. So again, gives you the idea of population growth and growing very, very, very rapidly. Okay. Anybody have any questions on any of those 3? Because for the most part, the applications you're going to do today, you're going to go through and you're going to figure out the equation, plug stuff into the right spot, and then evaluate with the calculator, get an answer. Okay. So let me give you the assignment, and then I do want to start you off on the first problem, only because my other class had a lot of questions right away, and I just want to clarify quickly. Okay. So here's your assignment, pages 194 and 195. You've got like 6 or 7 questions is all you have to do. Although the first couple have some parts to it. So 53 to 59 odd, 67 and 69. And like I said, I want to take a look at 53 quickly, just because I want to get you off to on the right foot, get you started correctly. I'm going to show you a little calculator trick too. That'll save you some time. All right, so here's what they have on 53. 53 and 55 look something like this, where they give you the principal, they give you an interest rate, they tell you that, in this case, it's 10 years later, and what they want you to find is if you only compounded once a year, how much money would you have 10 years later? If you compounded twice a year, how much money? 4 times a year, 12 times a year, all the way up to continuous, okay, the Pert Formula. So they're trying to get you to be able to compare the values. So, as we go back real quickly, which one of these formulas am I going to be using for most of this? Top or bottom? Top. Because it's not, until you get to the continuous part, the very last part of the table, you're using that top formula. So, let's set it up, and then I want to show you the calculator part of things, okay? Since we didn't do an example like this. So in this case, if we go through and we're going to set this up, we've got A equals, principal they give you, $2,500 is what we're starting with. Then in parentheses, we've got 1 plus the interest rate divided by the number of times you compound per year. Okay? Interest rate as a decimal, 2.5% is what as a decimal? 0.025, okay? Not 0.25, that's 25%. 0.025, okay? So we would do 0.025 divided by the number of times you're compounding, so it depends on which part, okay? We'll start with 1, and then I'll show you how you can easily fix it. So if we're only compounding once, we would just put over 1. And then the exponent in that formula is n times t. What that really represents, again, if I'm explaining what the exponents represent, n is the number of times you're compounding, t is the number of years. So the exponent is going to represent the total number of times you compound over the 10 years. So if I'm doing it once a year for 10 years, that means the exponent will be 10. When I go to the second part, if I'm doing it twice a year for 10 years, then the exponent becomes 20. 4 times a year for 10 years, then the exponent becomes 40, and so on and so forth. Okay? So there's the setup. Let me go to the calculator now so I can show you just a couple of things. So if we're going to type this in, 2,500 times, we'll put parentheses in, 1 plus. General rule on any calculator, anytime you put a fraction into the calculator, put it in parentheses. Okay? So I'm going to put, oh, no, I wrote it wrong. I said 0.025 and then I wrote 0.25 on the board. Oh well. 0.025 divided by 1. And now here's the first calculator part. I'm going to close the parenthesis, which is really just closing the parenthesis on the fraction. Then I need another parenthesis to close that quantity. Okay? Because it's that entire quantity that's raised to the power, not just the fraction. And now we raise it to, we said the power was, in this case, 10. And you hit enter, and there's your first answer right there. $3,200.21, round again to the nearest cent. So 10 years later, if you're only compounding once a year, you end up going from 2,500 to 3,200. Okay? Now, here's the trick that I think you'll appreciate. Rather than having to go back now and retype everything in, we can edit rather than retype. Okay? So if you hit the second button on your calculator, and then you hit the enter button, it brings up the same thing you just typed in, and all you have to do is go an arrow and change which numbers need to be changed. You don't have to retype it in. So now let's say we went to 2, which means my exponent now is 20 instead of 10. We're compounding 20 times now, twice a year for 10 years. And there's one other thing I have to change. What is it? The 1, right? We now need to divide by 2 instead of 1 because we're splitting it. So I can arrow back to that, change that to a 2, and now I can hit enter again. And there's the difference, compounding once a year to compounding twice a year. Same everything else. You got an extra $5. Okay. And now if you wanted to go to 4 times, again, second and enter. And now you can go back and edit the numbers again. Okay. Questions? Calculator questions? Anything? Otherwise, for that table, you can just keep going back and forth. Once you get it typed in, edit, get the next answer. Go back, change what you need to change, edit, get the next answer, and go from there. All right. So that is